This is going to seem completely random at first, but then it will grow into something useful. Once upon a time, there was an angle named theta, just sort of out there. We decided we would look at theta under the microscope of the unit circle because that's something we know something about. And we decided we would slide theta down into the standard position so that we could be talking about theta intelligently. What do we know about theta? Well, not too much, except that if it's on the unit circle, we know that cosine theta and sine theta are the coordinates of this point right here. If we draw a chord and label it d, the distance from this point to this point, right, the straight line distance, we know that the distance from here to here has to be the sine of theta, right? And this distance right here, right, from here to here is cosine of theta. From here to here is 1. So this distance right here is 1 minus cosine theta. And using the Pythagorean theorem, this squared plus this squared equals this squared. So we know that d squared is equal to sine squared of theta plus the quantity 1 minus cosine theta squared. If we take this and expand it, we get 1 minus 2 cosine theta plus cosine squared theta. Then we've got this cosine squared theta here and this sine squared theta over here, and if we put them together, they equal 1. We had this other 1, and then we had the minus 2 cosine theta. So when we get all done, d squared is equal to 2 minus 2 cosine theta. But let's remember, this is what happened to theta after we moved it. We didn't find theta sitting in the standard position. We found theta somewhere else altogether. We found theta here, where the two rays that made up theta were actually the terminal rays of two other angles in standard position. If this is angle A, this is the ray of angle A in terminal position. And if this is angle B, this is the ray of angle B in standard position. Which means, instead of calling them A comma B and C comma D, I can actually be a little more specific about the coordinates of these points. Yeah, they're just angles. They're just variables, right? I assigned A to this angle, and I assigned B to this angle, right? So now let's do the same thing we did a moment ago, and that is figure out the length of D when it's hanging out here instead of hanging out in standard position. The y-coordinate of this point is sine A. The y-coordinate of this point is sine B. So this distance right here is sine A minus sine B. And here, the distance from here to here, well, the x-coordinate of this point is cosine B. And the x-coordinate of this point here is cosine A. So cosine B minus cosine A will give me this distance. Sorry, the distance from here to here is that. This squared plus this squared, and then the square root of it, or d squared is equal to this. If I square this, I get sine squared of A minus 2 sine A sine B. Rearrange those. And put them together, and you've got 1 and 1, which of course make 2. And then you've got the minus 2 sine A sine B, and the minus 2 cosine A cosine B. Oh, look, we have two different ways to talk about d, or d squared. We said that d squared was equal to this, right, when it was over here. And then when it was over here, we said d squared was equal to this, and both of those simplified, and we got this. So those two things have to be equal to each other, because just moving theta didn't change the length of its chord. So what happens? Well, you divide everything by 2. I could subtract 1 from both sides. I could multiply both sides by -1. And I wind up with cosine of theta is equal to sine A times sine B plus cosine A times cosine B. Wait a minute. What did we say about theta? What is theta? Right? Theta is A minus B. And that means this. It's another identity. And if you pull out the book from beneath your feet, there it is. Page 201. Everything I just did, right? It's all sort of laid out here.